Okay, so today we're going to talk about which law. And talking about which law, what we're going to be looking at, we're going to be looking at your paper that looks like this. So you may have to flip your paper over so that you see this. Milan, you'll be fine, I promise. As we're looking at this short video about our Newton's laws, because talking about Newton's laws, what are we studying? What's the type of science that we're studying? Force and motion, but that falls under what type of science? Starts with a P. Physics. We're studying physics. And Newton is like a father of physics because he was a physicist, which means that he studied physics. He understood and force and motion. And so he came up with the 3 laws that we discussed before. So we're going to kind of put it back into perspective. We're going to start from there, and we're going to look at Newton's 3 laws so that we can go through and understand a little more before we continue to go forward. While you're looking at this short video, these 3 areas of boxes here on the screen, you're going to look at these 3 boxes, and you're going to try to fill in the blanks for Newton's first law of motion, Newton's second law of motion, and Newton's third law of motion. I'm not going to pause the video. It is going to go a little bit quicker, but just try to see how much of it you can fill in before we get started. If you look at the first box, really quickly because I want to fix something on there. It says an object at blank stays at blank, or an object that is blank at a blank. This blank here, the one that's after the words at a blank before the NA straight, this should be 2 blanks. So it should be an object at blank stays at blank, or an object that is blank at a blank blank. So where you see the red dot? Well, we're going to watch a short video. You're going to see what may go there. Any questions? So again, while we're watching the short video, you're going to pay attention to these 3 boxes and see if you can fill in the blank for those 3 boxes. Got it? All right. Then let's take a look at the video.
Things move and why things move? It was Isaac Newton who discovered the 3 laws of motion. He was a scientist who lived from 1642 to 1727. Let's first learn about the first law of motion. It is also called the law of inertia. It states objects will remain at rest or in uniform motion in a straight line unless acted upon by an external unbalanced force. To understand Newton's first law completely, we need to learn about inertia first. See, this is a very large sofa. What's special about it? It's stable. It is not moving. Now go ahead and try to move it. Oh, you can't. It's not willing to move. You can't move it as it is very large. Now try to move this small stone. Good. You can move it a little bit, but you had to put in a lot of effort. It was also like it didn't want to move from its original position. Even the smaller things don't want to change their positions. They don't want to move. Even a small stone takes some effort to move. This is the first rule of physics. Things like to stay where they are. No object in this universe would start moving unless some external effort is put on it. It's like all things in the world are lazy. Now the question is, if things are lazy and they don't want to move, then how does the movement happen? The answer is that there are so many things in the universe which push and pull other things and force them to shift their positions, like you forced the small stone to move. But as we said earlier, that things are lazy. They would try and stop their movement as soon as the effort was removed. Well, you'll be wrong if you think like that. You'd find it very strange to accept that when a small stone was still, it wanted to stay still. But once you'd put it in motion after putting some effort, it would like to keep on moving. In reality, it would keep on moving forever and ever. But somehow it stops. But it stops not because it wants to stop. It stops moving because things in its path force it to stop. Maybe due to air, or if it bumps into a tree or rough surface on the ground. But suppose there were no tree in its way, or there was no roughness on the surface, and also imagine that it does not have poles or trees in its way. The stone would never stop. it would keep on moving. It happens in outer space where there's no air or roughness. If you kick a small stone, it'd keep on moving and moving and would never stop. So how can we say that things are lazy? See, the small stone wanted to move forever, but it was stopped by the resistance of air, trees, or roughness of surface. It's like you moving on a slippery road. You'd keep on moving unless there was some effort put in to stop you. The same is true with a small stone in outer space. It would keep moving as nothing came in its way. It also doesn't want to stop as it is too lazy to do that. So now we can change the first rule of physics. Things want to stay in the position they are, to things want to keep doing what they're already doing. If things are at rest, they want to stay at rest. And if things are moving, they want to keep moving. In other words, things are lazy. So there's a lot of laziness in the universe. Physicists have a special name for this laziness. It is known as inertia. So now you understand Newton's first law of motion. Can you write it? Well, you are very much right. Now let's move on to Newton's second law. As we know from the first law that to overcome the inertia of an object, we have to apply unbalanced force. Newton's second law talks about how fast an object would move. Well, it states acceleration of an object depends on the mass of the object and the amount of force applied. In mathematical terms, Newton's second law states that force is the product of mass and acceleration. To cause an object to accelerate or speed up, a force must be applied. The more force you apply, the quicker you accelerate. Look at these two swings. If you apply the same force on both swings, check whose goes faster. Let's first push the little kid. See? It goes very high. Now push this fat man with the same force. See, it does not go far because it has more mass than the little kid. So the more mass there is, the force required to push the object is also greater. Let's look at the mathematical formula of the second law again. It's the product of mass and acceleration. We've already learned that if there's more mass in an object, to move it, we need more force. Now let's see this kid sitting in the swing. If we apply a little force, then it goes a small distance. Now if we apply a lot more force, it goes very high. So to get more acceleration, we need to apply higher force. So now you can understand the relation among force, mass, and acceleration. Until now, we've only learned the first and second laws of motion. Oh, you're riding a bicycle. Have you ever wondered why a bicycle moves forward? Well, it moves according to Newton's third law, which says that for every action, there is an equal and opposite reaction. To understand this, see what happens when you drop a tennis ball. As the tennis ball hits the floor, it causes a downward force on the floor. This is the action. The floor reacts by pushing on the ball with the same force, but in the opposite direction. Action, reaction. Together, the floor and the ball form what's called the action-reaction pair. So now how it applies to your bicycle. When you push the pedal, the parts of the tire which touch the ground push it backwards. The ground also pushes the tires forward with the same force. So the parts of tires and earth form a pair of action and reaction. So what happens to the earth when your tires are applying force to push it backwards? Nothing happens to it, since the earth is very big as compared to your bicycle. The force applied by your tires does not move it backwards, but force applied by the earth pushes your bicycle forward. So now you understand Newton's third law. Yep, the tennis ball is the right example. The ball and the floor are creating a pair of action and reaction.
All right. So now that we have that information about Newton's laws, and before you all are asking what am I doing, I do have these thick socks on my shoes because I'm trying to stretch them out, the shoes are new. So let's get over that hurdle. All right, so let's take a look then at our information in regards to Newton's laws. You didn't just see that, so hold on. Okay. Back. My apologies. I thought I cleaned the board. So with Newton's first law, who can help us out with this? Who can help us out? Come on. No, Marcel, I didn't call your name. You had your hand up. Yeah. Come on. And I'm going to put a color screen up here so that you can choose whatever color you would like. What happens when you pick up the pen, a color box will come there and you can choose whatever color you like. So if you pick up the pen and you can choose the color you want to write with. The first thing that you need to do is, no, drag that thing down. You have to read this aloud to us because right now you're the teacher. You need to read it aloud to us and with the blanks.
Okay, an object at blank stays at blank, or an object that is blank at a blank and a straight blank keeps moving at that blank unless another blank acts on it.
Now remember here, we have two blanks. Okay? So read it one more time with those two blanks.
An object at blank stays at blank, or an object that is blank at a blank and a straight blank keeps moving at that blank unless another blank acts on it.
That's okay. When she fills it in, she'll put it there. So go ahead and talk us through this.
Okay, so it states that an object at rest.
Okay, fill it in.
Will stay at rest. Or an object that is in motion.
In motion or moving. That means the same thing, right? Okay. At a blank blank.
Oh. Yeah.
No. If you know it once, you know it twice. So read it, start from the beginning again. Let's get it through. So Newton's first law states
that an object at rest will stay at rest, or an object that is in motion at
keep going.
An object at rest will stay at rest, or an object that is in motion will stay in motion unless acted on.
What you're missing something. An object that is in motion at a what, class? At a what? Something is moving, but it's moving at a
Direction.
what are you saying? Uniform what? I roll the ball. It's rolling. It didn't speed up. It didn't slow down. It's just rolling at a steady pace. Very good. So you just want to add put one word on the line and put the other word underneath it. If she said steady rate, would that mean the same thing?
Yes.
If she said steady speed, would that mean the same thing?
No.
If yes, pace, rate, speed. If she said steady velocity, would that mean the same thing? Yes, all of those words mean the same. So start from the beginning and walk us through.
So an object at rest stays at rest, or an object that is in motion at a steady rate in a straight line.
Line, very good. That's because no air or anything has been a force acting upon it.
Keeps moving at that rate.
Okay. If she said speed, would that be correct?
Yes.
If she said pace, would that be correct?
Yes.
If she said velocity, would that be correct?
No.
Yes, velocity and
yeah.
speed. Look at your dictionary.
Unless another force acts on it.
Exactly. Now, put your pen down, turn around, tell the class Newton's first law without looking.
An object at rest will stay at rest, or an object in motion will stay in motion unless acted upon by another force.
Now, the other force could be air. So if the air blows it, it's going to slow it down or speed it up. So therefore, it's an object not only that is in motion, but in motion at a steady pace in a
straight line.
Straight line. Very good. Let's give her a round of applause. All right. Now, before we move on, let's look at the law, Newton's first law, a little bit more. Can I have a volunteer? Marcel, come on up. Now, Marcel is going to be our magician. Let's give it up for the great Marcel. Chocolate drop. All right. I am Marcel's lovely assistant. Let's give it up for the lovely assistant. All right, Marcel, this is your magic trick here. Why don't you read aloud the directions on what it is that you're going to be doing? Yep.
Set the plastic cup on a flat surface and place the index card on top. Position the penny in the center of the index card. Use your fingers to pull the card so it slides off the cup. Tell students to keep their eyes on the penny.
Tell your audience to do what?
Keep your eyes on the penny.
Keep your eyes on the pennies. It's on the top of the cup. All right, you'll be able to see it. Are you ready? The great Marcel? Here we go. Marcel Dini.
1, 2, 3.
Now, Marcel. Ask the class this.
What happened to the penny when the card slid out from underneath it?
Talisha, what happened to the penny? The penny dropped into the cup. Did everyone see that? Okay.
How is this related to inertia?
He says, how is it related to inertia? How is this related to inertia? Guys, take a seat. There's nothing else to see right now. How is this related to inertia? Let's do some thinking.
Because it got speed. No, the penny is lazy and it didn't move.
The penny is lazy. It did not want to move. So therefore, it wanted to stay at its same spot. But we use force to remove what?
The card.
The card. So the card moved. The penny wanted to stay where it was. So therefore,
The penny fell into
the penny fell into the cup. Excellent. Let's give the great Marcel Dini a round of applause. All right. On page 23 of your notebook, so you have to open your notebooks up and turn to what page would be page 23. You may have to count it out. Let's do that quickly. And you want to label page 23, what did I learn? All right. Now that we're there, based on the demonstration that Marcel just showed us, where the card was slid from under the penny was there and the penny was at rest. And Miles told us that the penny was lazy, like a lot of things in nature. It's lazy. It doesn't want to move. So therefore, the penny had no force acted upon it. What had force acted upon it?
The card.
The card had force acted upon it. The penny had absolutely no force. So we moved the card. The penny wanted to do what? To stay at rest. So therefore, the penny did not move. The penny just dropped in the cup. That is because the penny had what?
Gravity.
The gravity did put it down. The penny had inertia. So let's write a little bit about inertia here. Inertia is going to state what? What does that mean? An object at rest will stay at rest. Excellent. Yes, you are. Now think about this. How many of you like roller coasters? Now when you get on a roller coaster and the guy's giving you the instructions on the roller coasters, what's the most important thing that he has to tell you? And the most important thing he or she comes around and does, Micaiah? They come and check for your seatbelt. Because of inertia. Why? Make sure you won't fall out. And not that you won't fall out because you're sitting there and playing around. When is it possible for you to fall out, Joshua? Hopefully your roller coaster does not crash. Hussein, When you go upside down or when you go up a hill and down a hill, they want to make sure that you stay in the car and not fly out the car, because not only does inertia state an object at rest will stay at rest, it also says or in motion will stay in motion. It is because of inertia you put seatbelts on in a car. It is because of inertia you put a seatbelt on in a roller coaster. Because of inertia. So we can say inertia is also known as what?
Acceleration.
Newton's first law. Now from the video, moving on to the second law. The second law is the most difficult law of Newton's laws. So we're going to talk about that in a little bit. But moving on to that law, there was one particular equation that they showed us in the video. It was about force. Now, thinking about your dictionary, we understand that force is a push or pull. Everybody do the dance with me. What's force? A push or pull. So therefore, the equation for force needs something. It is a push or pull, but what was that equation?
Force equals mass times acceleration.
Mass, excellent, times acceleration. What is mass? What is mass? Huh? Just give me one word what mass is, or something, a sentence that describes what mass is.
Weight.
Okay.
The weight of an object.
It's the weight of an object. Now let me just make that a little bit clearer. It's not necessarily the weight, because the weight is going to be different if we're on Mars. If you're on Mars, your weight will be different than your mass. Mass is actually the amount of stuff in an object. Weight is the gravitational pull on you. So Mars doesn't have gravity, so therefore your weight would be different on Mars, but your mass will be the same because you have the same amount of stuff. So we can say mass means how heavy you are. And that's perfectly fine. So when mass, we're talking about the heaviness of something. Acceleration, we're talking about, you're about to say it, the speed. So force is going to involve the heaviness and the speed of something. So how well you're able to push or pull something fast or slow is going to depend on the mass, the heaviness of something. Does that make sense? Like, for instance, if your mother or father says, hey, I need you to help me move this furniture around, or I need you to help me carry this new dresser in, or I need you to help me carry this furniture out, or help me change around your bedroom, that bed or that dresser that you're going to be pushing or pulling is going to depend on the heaviness of it. Go ahead and get tissue. The heaviness of it, and how fast or slow you're going to be able to do it is also going to depend on the heaviness, how well you're going to push. If you're pushing a couch and it's heavy, you're going to be like, because it's very heavy, it's not going to go very fast. But if you're just trying to push a chair, one little push is going to slide that chair across the room because it's not that heavy. So it's going to go very
Slow.
fast. Very fast. Think about what you're doing. All right. So then let's move on. May I have a second volunteer? Come on, Milan. No, you're up your nose. No, Milan, let's go. Move quickly, move quickly, move quickly. It's always a learning opportunity. All right, we're here to help you. Pick up a pen.
Okay.
And then you can choose a color. Under where it says property, slide that up. Choose whatever color you like. And then slide it down. There you go. All right. Shh, Donovan. Shh. Newton's second law. Read it aloud to us with the blanks.
Okay. The amount of blank needed to make the object change in blank depends on the blank
on the object and the blank required.
Okay, remember I said Newton's second law is the most difficult. Saying I'm talking. So the amount of blank needed to make an object blank is going to depend on blank and blank
I got it.
required. What do you need to do work? Because this is talking about work now. Force. You do need force. However, in order to be able to remember what force is what? A push or pull. In order to push or pull something, you need to be able to have, or you need to have energy. So the amount of energy, that's a pretty color. The amount of energy needed to make an object change its speed, also known as acceleration, also known as, that's with a V, velocity. Any of those words would be fine with speed. Because remember, a chair, a pencil, we can fling that across the room, but a couch, we can't fling that across the room. It's going to take more energy to be able to give it more speed. Okay? So, read it aloud to us with the words.
Okay, the amount of energy needed to make the object change its speed depends on the blank of an object and the blank required.
Okay, the blank of the object. How much energy you're going to need and how fast it's going to go. What is that going to depend on? Think about that couch incident or that pencil incident.
Math.
Thank you for yelling it out. You're such a ventriloquist. Not only are you a musician, but you're a ventriloquist. You just threw your voice up here. It's going to depend on the heaviness. So if something is very heavy, you're going to need a lot of
Mass.
If something is very heavy, you're going to need a lot of force, which means you're also going to need a lot of energy. And if you use a lot of force and you have a lot of energy, chances are it's going to move a little bit faster. So read it aloud to us and fill in the rest of the blank.
Okay. The amount of energy needed to make the object change its speed depends on the mass of the object and the blank.
What required? Stop yelling it out. She has to do it. Go ahead. Yes, she did.
I was about to say it.
Go ahead, Milan. Just write it. No, we don't use that word. All right, now turn to the class and tell us Newton's second law of motion. No. Look at it really quickly, then turn around and tell us. And it doesn't have to be word for word, because if you try to memorize it, you're not learning it. Remember, Newton's second law is going to depend on that moving of that furniture.
Okay, the amount of energy needed to.
No. Give it to me in your own words.
Okay.
Think about the couch. Turn around. Newton's second law. Tell me in terms of moving furniture around.
Well, you need the.
What do you need to be able to move furniture? No?
Okay, you need energy.
You need energy?
You need. Do I have to put it?
No, you don't have to have this word for word.
So you need force. Force. You need mass. You need energy.
You don't need mass.
I mean, not mass. Energy and.
Think about it this way. Don't try to memorize this. Tell me without using these words. When you push a couch, you have to be able to be strong, and all of us are strong because we all have, starts with an E, energy. And using that energy means that we're going, the only way that we can push, the only way that we can move that couch, either we're going to push or pull it. So for me to push or pull something, I need to have energy so that that thing that I'm pushing or pulling can move at a certain speed. And that speed that I push or pull it is going to depend on how the mass or how, you don't talk using the word mass, how what? How heavy it is. That's Newton's second law. Let's give Milan a round of applause.
Thank you.
On your paper, underneath or beside that block, you might want to write yourself a little reminder note. You might want to put something like moving furniture. Donovan. You might want to put a little note, maybe throwing a ball. Because a ball, if you try to throw a bowling ball, you're not going to be as successful with getting a bowling ball across the room as you are with getting a baseball or a football. That's because of Newton's second law. Got it? Any questions? Okay. Adam, are you awake back there? You with us? Okay. I'm going to move on to the next one. Come on, Makai. Newton's third law.
For every blank, there is a blank in blank action.
Also known as
Force.
force. Okay. And again, you can change the color if you like. You want to change the color?
For every action, there is a reaction.
Now, let me stop you for a second. If there weren't any more of those blanks, then that would be fine. For every action, there's a reaction. But a reaction is actually putting it in this blank. This is describing exactly what a reaction is. Cross that off. But, no, cross off reaction. Erase it. Newton's third law, let me make sure you're clear. Newton's third law, if it didn't have these blanks, if you were putting it in your own words, it would be for a reaction, there is a reaction. But reaction, we need to describe what a reaction is as opposed to an action. What is a reaction? What is it? What type of action is a reaction? If I put my hand out to shake your hand, you're going to,
React to
which means that you're doing the,
react. Opposite.
you're not doing the opposite. You're doing the,
Equivalent.
you're doing the equivalent. You're doing the equal, the same thing that I'm doing, right? But she's coming from an opposite direction. So for every action, there is an equal and opposite action. Let's give Makai a round of applause. And what I was saying to you is this entire portion equals the word reaction. It's acting to the action in an opposite and equal manner. Got it? Like, for instance, the bouncing ball. If I throw the ball on the ground, the ball hits the ground. The ground is hitting the ball back, which makes the ball bounce back to you. Got it? Any questions with that? Yes? No? Are you all with me? Okay, so now let's look at some illustrations which are numbered on your paper. The first one talks about this leaping frog. Read it for us, Tylisha, and tell us whether it's Newton's first, second, or third law. Number 1 on your paper.
A frog leaping upward off his lily pad is pulled downward by grabbing legs of another lily pad instead of continuing in a straight line.
Okay, look at it for a moment. Think about what you read and tell us, is that Newton's first, second, or third law? Number 1, the law we're reading.
First,
Newton's first law, why?
because it says it's pulled downward and the gravity lands on another lily pad instead of continuing in a straight line.
Okay, so what does that mean? An object in
Motion.
motion will stay in motion. Very good. So the first one is Newton's first law. Make sure you put a number 1 next to that. Milan, what's the problem, honey? What were you just working on? It's on the back of the paper. It's on the same side of the paper we're just doing. It's number 1. Flip it back over. Flip it back over. The same side with the 3 boxes. Number 1. Number 2. Read it for us, please. Carlos. Look at your 3 laws, take a moment, think about it, and then tell us which law is that. Why does that happen? Because of which law? Second one, does that involve anything with speed and mass? Is it talking about the rocket being heavy and that's why it takes so long to get it because of the amount? No, not that one. Look at what it says. The key words there says, the force of the gas expansion and explosion pushes out the back of the rocket and pushes the rocket forward. So you got something pushing down and you got something pushing the other way. Which is, for every action, there's a reaction. So this one is the third one. Very good. Urel, read this one to us. Read it loud so that the speaker will pick you up.
When you are standing up in a subway train and the train suddenly stops, your body continues to go forward.
Has this ever happened to anyone?
Yeah.
And maybe not on the train, but maybe in the car.
Yeah.
Maybe on the bus.
Yeah.
Why, Urel? Why does this happen?
Because
Because of Newton's first law, which is also known as the law of inertia. This is number one, the first law. All right? Michaela, read to us number 4.
After you start up your motorbike, as you give it more gas, it goes faster.
Take a moment, think about what you read, look at the 3 laws, and see which one does this, why does this happen? Because of which law? It's talking about speed, and it's talking about adding some force. The amount of force you add is going to depend on the speed of that bike. The second law, Newton's second law. Why is it that when this guy turns right, his body goes left? What law is that? He started off going straight. He turned right, but his body is going the opposite way.
Oh, first.
It's the first because an object at rest or an object in motion will stay in motion. He was going straight. The car turned left. His body still wanted to go straight, so it looks like he's turning right. Or vice versa, right and left. Understand?
Yes.
Which is why when your parents turn the car really quickly, your body goes this way. All right. For the next one, Donovan. This is number 5. Come on, Donovan, read it. Can't hear you. I know you can speak louder. Gently. As you can see, the one at the top is the gentleman throwing a baseball because he's a professional ball player, and the one at the bottom is a little baby throwing a baseball. Which law is this? It's talking about the mass. It's talking about the speed, how much energy. The second one. Obviously, the professional ball player is going to pitch it a lot farther and a lot faster than the smaller one because of the amount of force that is applied to it. All right, question. I don't have the 2. Now that you raise your hand though, Miles, you can read us number 6 and give us the answer for that. 5 was Newton's second law of motion. Miles, read us number 6.
Oh, hey, swim, pitch water back, about her body moves forward.
Everyone be a swimmer now. Take your hands and do the breaststroke. Push your arms back. But you got to really do it because when you push your arms back like this, what's happening with your body?
It's going
Forward. Your arms are going back, but your body's going forward. Miles, which one is that?
I think it's,
Shh.
well,
Our arms are going back.
I think it's
2. And we didn't talk anything about speed. We didn't talk anything about the amount of force required to make her go faster. We talked about the direction her arms were going and the direction her body was going.
I mean, number 1.
No, we didn't talk about her stopping or bumping into anything and her body flying back. Guys, be quiet for a second. We talked about one direction and a different direction. Why do you say 3?
Because
Because why?
it got a action.
What action? Right. But what is her arms doing?
Moving back.
Moving backwards. What's the opposite of backwards? And what's her body doing?
Moving
Moving which way?
forward.
Forward. So you have one action moving backward and the other action moving.
Backward.
You have one action moving backwards and the other action moving forward. So therefore, Miles Newton's third law is what? Miles Newton's third law is what?
For every action, there is a equal
Should be quiet for us.
and opposite.
Do you understand why that one is the third law?
Oh yeah, I got you.
Okay, very good. Number 7, Barbara.
As an ice skater pushes harder with his leg muscles, he begins to move faster.
The second law, why?
Because he's going faster.
Because he's going faster and it's talking about the amount of what used? The amount of what used? Energy and force. Got it? Questions? Okay. Hussein, number 8.
When Bobby, age 5, and his dad are skipping pebbles on the ground, the pebbles and Bobby's dad go farther and faster than they.
Everyone knows what skipping pebbles are, right? When you throw the pebbles on against the water and it hits the water and keeps bouncing. All right, Hussein.
Second
Why?
one,
Force required, and it's talking about, kind of talking about speed because it's going a little farther, but yes, force required. So this is the second law of motion, Bobby and his dad skipping pebbles. Number 9, Katara. We just did number 8. I just said it was the second. You got to pay attention. Katara, read us number 9.
When you pedal a canoe, the canoe goes fast.
Canoe. Everyone pedal canoe. You pedal canoe by, you take your arms and you do this. And then you do this. Everyone pedal canoe with me. When you pedal a canoe, it goes faster. Now, if I was different and I was just doing this, and I only had one other person, or you can do this with it. But if I was just that one person and I was just pedaling lightly like this, my canoe would not go as fast. I was really doing it, or really doing it, then my canoe would go faster. Katara, which law is describing this? I just said about how much pushing I'm putting. Pushing there is describing what? Pushing is describing a force. I said if I push very hard, I'm going to go faster, which is also known as speed. Therefore, Katara, which law is it? Number 2, because it's talking about the amount of force and the amount of speed. Number 10. Stop sucking your teeth when I don't
A
call.
little girl who has been pulling the sled behind her in the snow is crying because when she stopped to tie her hat on, the sled kept moving and hit her in the back of her leg.
So then this is the little girl. She's pulling the sled, and then she's like, oh my head. What's happening? She's getting hit with that sled. You think that sled is mad at her? Is that sled bullying her?
No.
Did she talk about that sled earlier and the sled heard about it and now it wants to fight her?
No.
But what's wrong? Why does the sled keep hitting her? Say it louder, Anaya. An object at motion stays at motion. She's pulling that sled. Is she in motion?
No. Yes.
Is the sled in motion?
Yes.
She stopped. What did the sled want to continue to do?
Going.
It wanted to continue doing it. It didn't get the memo that, hey, we're stopping here. So the sled kept moving until it hit her leg. And then it stopped. Did the sled apologize? No, because it can't apologize, duh. So therefore, what law is this? The first law, because an object in motion stays at motion. Any question? Yes.
What was number 2?
You tell me.
3.
Number 2 was as a fuel rocket. Remember, it pushes the force out and then it goes forward. All right. If you flip your paper over, you have something that looks like this.
That's how it works.
Class is not over. Right now, you're going to work on. You're going to work on this with your partner. The first thing you need to do as working on it is, there's words here. When there's words on papers, you better read it. You start from the very beginning, you read it all the way through. In reading it all the way through, then you will complete this part. If you look here where it says at the very bottom, fill in the missing words to complete the sentences about Newton's first law of motion. You got that? Then it says, then copy the box letters. Cross that part off that says then, cross off these words that I say. Then copy the box letters on the lines below to solve the puzzle. Cross off those words. You don't need box letters to be able to solve that below puzzle. We've talked enough about it where you will know what that is. So you're going to work on this with your partner. What you do not finish will be homework. So you have enough time to complete your homework. When you are finished, do not glue this paper in your notebook at all. Bring it to me. You'll glue it in after I've graded it. Any questions? And this concludes this lesson.